Hi. Look. This is a space and time diagram. And this is a trajectory in space-time. This is not a trajectory in space. Or is it? Do we actually need time in physics? Do we actually need time in reality? There is a philosophy today which is eternalism, which says that time does not flow, that every event exists now. Past is still happening and the future is already happening and they will always be happening. Which means that now is treated like here. The past and the future are places in the space. Time is treated like space according to eternalism. Indeed, this philosophy is usually associated to modern relativity, but actually it perfectly works also in a Newtonian classical space-time. I had developed an eternalist point of view on my own 8 years ago, and I didn't know about relativity, and I was thinking about a Newtonian space-time, and it perfectly works. So we should start by there. This is the thought experiment I usually make to show how fictitious is the flow of time. Let's say you want to build a machine which reverses the time flow. First, you start building it, then you end building it, then you activate it, and then you end building it, and then you start building it, because you reversed the flow of time. So now time is flowing towards the past. But you didn't notice anything, because if time flows backwards, your brain flows backwards, your memory flows backwards. How can we be sure that time is flowing if we can't even tell in which direction is it flowing? So let's see now if we can find an equivalence between space and time. Here we have the Galilean transformations from a frame S to a frame S first, which is moving at speed v. These transformations say that we must have a shift of an angle phi, such that the tangent of phi is the speed v, between the t and the t first axis, which means the space is not the same for both the systems. Instead, the space axis is the same for both the systems, which means the present is the same for both the systems. So space and times are clearly not symmetric in this transformation. But what if we are just using the wrong units of measurement? Maybe there exists a constant c, let's say that c stands for constant, such that if we multiply time by c, we also get a shift in the x-axis. And let's take c such that this shift is of the same angle for both space and time, so that we have symmetry with respect to the bisector. First, let's make some qualitative considerations. To notice the change in the x-axis, we multiplied t by a very large constant. So we are dealing now with very large, very high speeds. And we are assuming symmetry with respect to the bisector. And the bisector, we can see, it represents a particle moving at speed c. Now, if our system as first is moving also at speed c, we see that the time and the x-axis coincide, and we expect a singularity in our equations of transformation. But the interesting part is when the velocity of s first is greater than c. We have here the time axis and here the space axis, but if time and space are the same thing, can we really distinguish between the space axis and the time axis in this case? Actually, the situation is equivalent to that, with the speed being smaller than the speed of light. Being a time axis and a space axis depends therefore on where you are in this diagram. If your axis is here, then it is a space axis. If it's there, it's a time axis. Indeed, this is called the space-like zone, and this is called the time-like zone. This also means that we can't have frames of reference moving at a speed greater than c. So we have a limit speed. This speed happens to be the speed of light, but that is not important now. We can now start writing our linear transformation. This is the general formula for a linear transformation for the x first axis. But if time and space are equivalent, and by our assumption they are symmetric with respect to the bisector, then we can exchange ct with x in our transformation and get the transformation for the time axis. So we now get this matrix of transformation, which is a symmetric matrix with a homogeneous diagonal. But now we need a second action, and this action will be the action of the relativity of transformations. If we apply the transformation L, we have determinant, this transformation has determinant D, and if we apply the transformation L to the minus 1, so the inverse transformation, we will get a determinant of D to the minus 1. We don't want to have a privileged transformation between one transformation and its inverse. So these determinants should be equal. So we should have determinant 1 in every of our transformation. The determinant being equal to 1 gives this relation, which can be written in parametric form with parameter phi using the hyperbolic functions. The sign is not very important. It will only determine the direction in which the frame as first is moving. By convention, we put here minus sign, so this will resemble more the Galilean transformation. And this is our matrix now. We obtain this matrix by using our two axioms: time, symmetry between time and space, symmetry with respect to the bisector, so time and space being interchangeable in our equations, and the determinant of transformations being 1. So our transformation is a hyperbolic rotation in space-time, which is pretty cool. And it's also the Lorentz transformation, although it's written with angle phi instead in terms of the velocity v. To obtain the velocity v of the frame as first, we apply the inverse transformation. So we change t of s first with and x of s first with x first of s first and t first of s first. But x first of s first is the position of s first measured by s first itself, so it is 0. And we obtain this relation for the velocity. The velocity v is c times the hyperbolic tangent of phi. And from this we can obtain the hyperbolic sine and the hyperbolic cosine, and we can write the whole transformation in terms of the velocity v instead of the angle phi. So we obtain the Lorentz transformations written in terms of the speed v, and we obtained them by using these two axioms, that space and time are interchangeable in our equations, which means symmetry with respect to the bisector, and that the determinant of the transformations is equal to 1. Now the first axiom is usually replaced by the constants of the speed of light, from which follows that time and space are interchangeable. However, I think the other way around, as we did, is more profound, because a more profound reason for relativity is looking for a representation of time which is equivalent to space, which is exactly what we did, and which led us to the Lorentz transformations. So we got rid of the concept of time in physics.